The interrupting current rating of a circuit breaker is the maximum current it can safely interrupt without sustaining damage. It is typically expressed in kiloamps. To calculate the interrupting current for a circuit breaker, you must firstly determine the short circuit current. Calculate the maximum fault current that can flow through the circuit protected by the circuit breaker. This involves considering the power source characteristics, circuit impedance, and any other factors that could contribute to the fault. Secondly, apply a safety factor. Multiply the short circuit current by a safety factor to account for potential variations and uncertainties. A common safety factor is 1.25. Thirdly, choose a circuit breaker. Select a circuit breaker with an interrupting current rating greater than or equal to the calculated interrupting current with the safety factor applied. It is not appropriate to use a 277-volt circuit breaker for a 120-volt system. Circuit breakers are designed for specific voltage ratings, and using a higher voltage breaker on a low voltage system can be dangerous. A 277 breaker is designed for a higher voltage system. Using it on a 120-volt system can cause the breaker to trip prematurely due to oversizing. Circuit breakers use specific arc quenching mechanisms designed for specific voltage levels. A 277-volt breaker may not be able to effectively interrupt the arc in a 120-volt system, increasing the risk of damage or fire. Most electrical codes prohibit the use of circuit breakers with voltage ratings that exceed the voltage of the system they are protecting. To further elaborate on calculating the interrupting current, let's delve deeper into each step. When determining the short circuit current, you need to consider several factors. Firstly, the available fault current from the utility transformer. The utility company can provide this information, typically expressed in amps at the transformer's secondary terminals. This represents the maximum current the utility can deliver under a fault condition. Secondly, the transformer impedance. The transformer's impedance limits the fault current. Lower impedance results in higher fault currents. This impedance is usually expressed as a percentage on the transformer's nameplate. Thirdly, the conductor impedance. The impedance of the wires and cables between the transformer and the circuit breaker also limits the fault current. Longer conductors and smaller conductor sizes have higher impedance. You can calculate conductor impedance using tables found in the National Electrical Code, specifically Chapter 9, Table 9. Formula involves the conductor's resistance and reactance per foot, multiplied by the conductor's length. Fourthly, other components in the circuit. Devices like reactors and current-limiting fuses also add impedance and reduce fault current. Their impedance value should be included in the calculation. To calculate the short circuit current at the circuit breaker, you can use the following formula: fault current equals source available fault current divided by the total impedance. The total impedance includes the transformer impedance and the conductor impedance. To apply a safety factor, multiplying the calculated short circuit current by a safety factor ensures that the circuit breaker can safely interrupt the maximum possible fault current, even with variations in the system. A safety factor of 1.25 is commonly used, but a higher safety factor may be appropriate in certain situations, such as when the system is subject to frequent voltage fluctuations or when the consequences of a circuit breaker failure are particularly severe. This helps account for inaccuracies in the calculations and potential increases in fault current due to future system modifications. When choosing a circuit breaker, select a circuit breaker with an interrupting current rating greater than or equal to the calculated interrupting current with the safety factor applied. The interrupting current rating is usually marked on the circuit breaker's label in kiloamps. It is critical to select a circuit breaker with an interrupting current rating that exceeds the calculated fault current. Using a circuit breaker with an insufficient interrupting current rating can result in the circuit breaker failing to interrupt the fault current, leading to equipment damage, fire, or even personal injury. For example, if the calculated interrupting current with the safety factor is 8 kiloamps, you should select a circuit breaker with an interrupting current rating of 10 kiloamps or higher. It is important to understand why using a 277-volt circuit breaker on a 120-volt system is unsafe. Circuit breakers are designed for specific voltage ratings, and using a high voltage breaker on a low voltage system can be dangerous. The voltage rating of a circuit breaker indicates the maximum voltage at which the breaker can safely operate and interrupt a fault. Using a circuit breaker with a voltage rating that is too high for the system can result in the breaker not functioning properly, leading to equipment damage, fire, or personal injury. The oversizing issue means a 277 volts breaker is designed for a higher voltage system, therefore using it on a 120 volt system can cause the breaker to trip prematurely due to oversizing. Circuit breakers are designed to trip based on both current and voltage. If the voltage is significantly lower than the breaker's rating, the breaker may interpret normal current fluctuations as an overload condition, leading to nuisance tripping. Arc quenching is another important aspect. Circuit breakers use specific arc quenching mechanisms designed for specific voltage levels. When a circuit breaker interrupts a fault, an arc forms between the contacts. The circuit breaker uses various methods to extinguish this arc, such as arc chutes, magnetic blowout, or gas-filled chambers. These arc quenching mechanisms are designed to operate effectively at a specific voltage level. A 277 volts breaker may not be able to effectively interrupt the arc in a 120 volt system, increasing the risk of damage or fire. The lower voltage may not generate a strong enough arc to be effectively quenched by the breaker's mechanism, leading to a sustained arc and potential damage. Code compliance is paramount. Most electrical codes prohibit the use of circuit breakers with voltage ratings that exceed the voltage of the system they are protecting. The National Electrical Code, NEC, specifically addresses this issue in section 240.83 marking. This section requires circuit breakers to be marked with their voltage rating, and it prohibits the use of circuit breakers with voltage ratings that are not compatible with the system voltage. Using a circuit breaker with an improper voltage rating violates the NEC and can result in fines, penalties, and even legal liability. Consider a scenario where a 277 volt circuit breaker is installed in a 120 volt circuit. A short circuit occurs in the 120 volt circuit, drawing a fault current of 5 kA. The 277 volt circuit breaker is not designed to effectively interrupt an arc at 120 volts. The arc quenching mechanism is not optimized for this voltage level. As a result, the arc may not be extinguished quickly, leading to a sustained arc. The sustained arc can generate intense heat, melting the circuit breaker's internal components and potentially causing a fire. Additionally, the excessive heat can damage the wiring and equipment connected to the circuit, leading to further damage and potential injury. In contrast, if a 120 volt circuit breaker with an appropriate interrupting current rating is installed in the same circuit, it would quickly and effectively interrupt the fault current, preventing damage and injury. The 120 volt circuit breaker's arc quenching mechanism is designed to operate effectively at 120 volts, ensuring that the arc is extinguished quickly and safely. In summary, to calculate the interrupting current for a circuit breaker, you must firstly determine the short circuit current, secondly apply a safety factor, and thirdly choose a circuit breaker with an appropriate interrupting current rating. It is also critical to understand that using a 277 volt circuit breaker for a 120 volt system is unsafe and violates electrical codes. Always select circuit breakers with voltage ratings that are compatible with the system voltage to ensure safe and reliable operation.